So let's start, colleagues. Dear tribunal members, dear participants, quorum of the meeting of the dissertation tribunal, the group of specialties, physics, nuclear physics, technical physics, physics and astronomy, radio engineering, electronics and telecommunications, material science and technology of new materials, thermal power engineering and physics, is present on June 22nd, 2022. All the tribunal members at the tribunal meeting, there are 5 permanent members present out of 5, together with 5 temporary members. The minimum quorum to start the tribunal meeting is 7 members overall. So I propose to start the work of the tribunal. Any objection? So no objection. The tribunal meeting is thus declared open. Everyone has an agenda. The first issue on the agenda is the thesis defense of Albina Serikbolova entitled Brains and Monopoles in Modified Gravities and Young-Mills Theories, and submitted for the degree of the Doctor of Philosophy in Specialty Physics. The work was carried out at the Department of Theoretical and Nuclear Physics of the Faculty of Physics and Technology at Al-Farabi Kazakh National University, the Ministry of Higher Education and Science of the Republic of Kazakhstan. Scientific supervisors: Vladimir Janushaliyev, Doctor of Physical and Mathematical Sciences, Professor of Al-Farabi Kazakh National University, and Yota Kunz Dolshagin, PhD Professor at Karlsruhe Ossietzky University of Oldenburg, Germany. So official reviewers: Konstantin Zloshastyev, PhD researcher at the Institute of System Sciences, Durban University of Technology, Durban, South Africa; Douglas Alexander Silgiton, PhD professor at California State University, Fresno, United States. Official reviewers are present. The thesis is to be defended for the first time. All tribunal members were provided with necessary corresponding materials. Do tribunal members have any comments on the agenda? No comments, so the agenda is approved. To get us acquainted with the personal profile of the PhD students, the floor is given to the Scientific Secretary of the Tribunal, candidate of Physical and Mathematical Sciences, Farida Belisarova. Please.
Dear members of the Dissertation Council, let me acquaint you with the materials received by the Dissertation Council from the applicant Serikbolova. An application addressed to the chairman of the Dissertation Council on the acceptance of the thesis for defense. Dissertation in Kharkova and on an electronic medium. Information about the doctoral student Serikbolova Albina Askarna, Kazakh, 1994 years old, place of birth Almaty region. She has a higher education, graduated from the Al-Farabi Kazakh National University, bachelor's degree in physics in 2017, master's degree in the double diploma program at the People's Friendship University of Russia in physics in 2019. She is unmarried. Personal sheet certified at the place of study by the personal service of Al-Farabi Kazmu, a copy of bachelor's and master's diploma with annexes, a copy of transcript in 3 languages on the development of the professional curriculum of doctoral studies, certified at the place of study, reports from domestic and foreign scientific consultants, certified at place of work of consultants, and extraction from the protocol of the meeting of the department where the dissertation was performed with a positive conclusion and recommendation for defense approved by the Vice Rector for Research and Innovation of Al-Farabi Kazakh, and the note sheet reviews of official reviews, a certificate issued by the National Center of Science and Technology Evaluation for anti-plagiarism, reference from the scientific library of Al-Farabi Kazno on the delivery of the dissertation and annotation, extraction from the protocol of the meeting of the Academic Council of Al-Farabi Kazno on the approval of the topic of the dissertation and scientific consultants, extraction from the order of the rector of Al-Farabi Kazno on admission to the defense of the dissertation, a list of scientific works certified by the scientific secretary of the Faculty of Physics and Technology of Al-Farabi Kazno and their copies. She has 8 published scientific works, including 3 articles in journals of foreign countries with high impact factors included in the International Information Resource Web of Knowledge and Scopus, 2 publications in Kazakh journals, which are recommended by the Committee for Quality Assurance in the sphere of education and science of the Ministry of Science and Higher Education of the Republic of Kazakhstan, 3 works in the collections of international scientific conferences, submitted materials by the applicant Serikbolova, complete with the established provisions of the state mandatory standards of education 2011 on the design of the dissertation for defense of the material for control on the field of education and science of the Ministry of Education and Science of the Republic of Kazakhstan.
Thank you. Dear colleagues, any questions to the secretary or the applicant? So no question. To present the main content of the thesis, the floor is given to the applicant Albina Serikbolova. Up to 20 minutes, please.
Thank you, Asghar Yerbulovich. Excuse me, do you see the screen?
Yes, we see.
Okay, thank you. So let me start. Good morning, dear professors and members of the Dissertation Council. My name is Serikbolova Albina Asgarovna, and I am a PhD student of specialty physics. Scientific supervisors are Professor Junshaliyev Vladimir Jumakadyrovich and Professor Yuta Kunz. The topic of my research is called Brains and Monopoles in Modified Gravities and Young-Mills Series. So let me start by considering the overview of the research. Sorry. Okay, so first of all, I would like to say that my talk will be in 7 parts. First of all, I have to set up goals and tasks of the research. After that, I have to discuss the relevance of the topic. The third one, I have to present you provisions which have to be defended. And also, if you notice, my work actually consists of the 2 parts, so 2 concepts, brains and monopoles, and I have to present the results for brains and results for the monopole-like spinor field solutions. To draw conclusions, and also I will show you articles which were published during 3 years of study in PhD. Okay. First of all, let me start from considering goals and tasks of the research. Firstly, I have to obtain and investigate regular solutions which describe brains in multidimensional space-time in the framework of this modified series of gravity. So this one. And secondly, I have to obtain and investigate topologically trivial monopole-like solutions in the framework of SU2 Young-Mills theory with including nonlinear spinor fields. And finally, and the last but not least, we have to demonstrate that the energy spectrum of our solutions has a mass gap. So provisions which have to be defended. There are 3 provisions. Provision number 1. In the theory of gravity with modified Lagrangian with type, there are branes with anti-de Sitter asymptotics and with a special point located at the center of the brane and existing in the following range of parameters. So as you see, n have to be less than 2 and greater than 1. Provision number 2. SU2 Young-Mills theory with a source of doublet nonlinear spinor fields leads to the existence of topologically trivial monopole-like objects with such asymptotic behavior of the magnetic field. And the last provision. Young-Mills monopole with a source of nonlinear spinor field has a minimum in energy spectrum, and thus that minimum we can interpret like a mass gap. So here I have written two values for the ground and for the first excited states for the parameter E. And the appearance we can say because of the consequence of nonlinearity of their fields. So let's start from provision number 1. In the provision number 1, I actually study brane solutions in modified theories of gravity. So that's why for explaining you the relevance of the topic, I have created such illustration, and I will try to explain you motivation for studying modified theories of gravity. So here is, you see the picture where we have a number of reasons to use modified theories of gravity. And firstly, first and foremost, as you see, modified theories of gravity, they're gravitational alternative for dark energy, so for explaining accelerated expansion of the universe. Secondly, some cosmological effects, for example, dark matter, can be explained in the framework of this theory. Thirdly, also can be useful in high energy physics, for example, for explanation the hierarchy problem of elementary particles. And another good point about modified theories of gravity, that with the framework of this series, it is possible to obtain some astrophysical objects like branes, which is one of the main goals of our study. In the next slide, I also tried to create some flow charts to show you families of modified gravity series. So as you see here, we have series with extra fields like scalar, vector, tensor, and mixed one, series with higher order derivatives, non-local series with higher dimensions, and other series with including torsion. And here I would like to highlight that we seek brane solutions in this theory with higher order derivatives, and we have chosen the simplest type, which was firstly introduced by Starobinsky in 1980. So this is the F(r) modified theory of gravity. Now, so we seek brane solutions in modified gravities. So of course we have to give a definition of the concept of the brane. So concept of the brane is actually very popular in modern physics, especially in general relativity and in string theory. So that's why I have divided this concept into two parts. So in the first picture, as you see, it's definition of the brane or brane world scenario, sometimes they call it, in the general relativity. So according to the Randall and Sandrom authors, our universe can be considered like a brane, so 4 dimensions hypersurface, which is embedded in some multidimensional space bulk. According to the string theory, if we look at the second picture, there is the concept of the D-branes. As you see, D-branes, they are attached to the ends of the string and can move in some enveloping space. So to conclude, we investigate in general branes with codimension 1. Yeah, so for investigating brane solutions in modified gravities, action without matter will look like this one, formula number 1. And here is F(r), it's some arbitrary function of the scalar curvature, Ricci scalar. So here is, we have chosen such type of modified gravity minus alpha(r) to the power n. And later, we will show that there are some ranges of n that don't contradict the observational data. After brane this action of modified gravity series, we can obtain a equation of modified series of gravity. And as you see, equations of modified series of gravity have been rewritten in the form which is analogically looks like Einstein equations. So on the right side, we just recall it like the source of effective geometric matter. But here I would like to highlight one more time that with the vacuum brane solutions, there is no any source of matter. So for brane with codimension 1 in n-dimensional space-time, we write down here metric, which has such form. And also I have present to you here the components of the curvature tensor and curvature scalar, so these components. And after substituting this metric and components of the rigid tensor and scalar to the above equations of modified series of gravity, we can obtain the equation of motion, number 7 and number 8. And here is, we have chosen actually equation number 8 like a main equation because of the two reasons. The first reason for choosing this type, because it's actually much simpler than the equation number 7. As you see here, we have the third derivative of the beta function, but here, as you see, we have the fourth derivative, so it's much simpler to investigate it. And the second reason for studying equation number 8, because actually equation number 7 is the consequence of the equation number 8 according to the Bianchi identity. So we will study equation number 8. So the solution at the origin aligned with the center of the brane we seek in such series, and here we set beta 0 is equal to 0, and here we have some coefficients, some constants, sorry, delta and gamma, and these parameters describe the behavior of the system near the origin. And after that, we substitute this expansion, number 9, into the above main equation 8, and in order to ensure finiteness of the derivatives, we have to equate to 0 these coefficients, and we obtain the following expression for the parameter delta. So delta have to be this one. Also, in order to ensure the regularity of the equation number 8, it is necessary that this delta have to be greater than 3. Using this condition and condition number 9, we can find that the n, which is actually defines the type of modified gravity, have to be in this range. So it have to be less than 2 and greater than 1. Next, here you can see some behavior of the functions like beta prime with respect to the xn. And in the first picture on the left side, it was plotted for the different values of the delta parameter, as you see these values. And on the right side, you see for the different values of the gamma parameters. What we can see from this figure, we can see that our solutions are with anti-de Sitter asymptotic, so the beta function tends to the constant. In the next figure, we have plotted the value of the effective energy density depending on different values, as you see in the first picture, for the different values of the parameter delta, and on the right side for the different parameters of the gamma. So as you see, it's also some interesting consequence of solving equations. The effective energy density here takes negative values. Here is also we constructed the phase portraits. In phase portraits, in our case, it's dependence of beta double prime from beta prime, depending on different values of the parameter delta and gamma. And as you see from phase portraits, we can take information about special points of the brane. So here we have some special points which describe our system. And also, I would like to show you the behavior of the beta function, the phase portrait, which is the middle picture, and the last picture is the value of the graph of the effective energy density for the different values of the dimension of space-time. So here we have chosen 4, 6, 8, and 9 dimension of space-time. So that brings me to the end of my first part of the research. So we have found regular flat symmetric brane solutions in vacuum. All these solutions have anti-de Sitter asymptotics. Also, we have shown that these solutions can exist only in some special choices of the parameter E. So as you see, it have to be less than 2 and greater than 1. And from physical point of view, we can say that these brane solutions can present a model of our universe like a brane with codimension 1. Now, let's move to the provision number 2. In the provision number 2, we study monopole-like object. So here is in this picture, I would like to explain you the relevance of the second part of my research. So in the second part, we talk about magnetic monopoles. And for example, in particle physics, magnetic monopole, it's hypothetical elementary particle with radial magnetic field. And that's why I have created such illustration to show you some historical background and some interesting searches for magnetic monopoles. So in 1894, Pierre Curie thought that by adding, as you see on the right side of the Maxwell equation, the density of magnetic charge, it makes Maxwell equation symmetrical. After that, in 1931, Dirac proposed his monopole for explaining quantization of electric charge. In 1974, Hooft and Polyakov independently, they have found monopole solutions in gauge theory. And here is relatively new research in 2016, gravitating Proca monopole in Einstein non-abelian Proca theory. Here you see some interesting searches for magnetic monopoles, like creation of synthetic magnetic monopole by Bose-Einstein found that like superfluid helium droplets can behave like magnetic monopoles, like in spin ice, some searches for magnetic monopoles, and a lot of searches in colliders. And 90 years have passed, but there is no evidence for these particles. And of course, they are of great interest. So we will study monopole-like solutions in this theory. So we study monopole-like solutions in non-abelian Young-Mills theory with including nonlinear spinor fields. For this reason, we have Lagrangian. So the first part related to the non-abelian Young-Mills field and 3 others related to the nonlinear spinor fields, where this term is nonlinear part of the spinor fields. And the corresponding field equations have this form. Equation number 12 related to the, it can be considered like the Young-Mills equation with the source, as you see on the right side, we have the source of monopoles. So we can say that the source of magnetic monopoles is the nonlinear spinor field. So it's like density of magnetic charge in here. And equation number 13 is nonlinear Dirac equation because we have this nonlinear term. Okay, so also for seeking particle-like solutions, we have to write down ansatz for SU2 monopole and spinor field. So we just take an ansatz of the Hooft-Polyakov. And here E, as you see, it's a spinor frequency, and functions U and V depend on the radial coordinate. And after substituting this ansatz and to this equation 12 and 13, we can obtain equation for unknown functions F, U, and V. So this is 3 main equations that we are going to study. The first equation can be considered like nonlinear generalization of Maxwell equation. As you see, this part can be called like density of magnetic charge, and 2 others show us how spinor fields behave yourself in our research. And one can suppose that these solutions describe some quasi-particle monopole-like plus C-quark system in quark-gluon plasma. So as you see in this equation, in the denominator, we have X term. So that's why we introduce boundary condition near the origin in the form of the Taylor series, as you see this Taylor series. And we solve these 3 equations, numerically as an eigenvalue problem for the eigenfunctions. Eigenvalues F2 and U1, and eigenfunctions U, V, and F. And here is, in this figure, I would like to present you the behavior of these eigenfunctions, U, V, and F. So in our case, we can say that F describes magnetic field in our theory, and combination of U and V describes the density of magnetic charge. And all these graphs have plotted for the different values of the spinor frequency A, E. Here you can see the table with the computed values of the system of the parameters. So we have here E, which is the spinor frequency eigenvalues. And also here we would like to present you the value magnitude of the total energy of the system for the different parameters of the E. What's more interesting about this theory? It is interesting to consider the behavior, asymptotical behavior of the radial magnetic field. And as you see, in our case, it decreases like R cubed, which is actually different from Hooft-Polyakov monopole, whose magnetic field decreases like R squared. Also, we have non-zero tangential components of the magnetic fields. And here, I would like to present you the distribution of the color magnetic fields. Yeah, so on the left side, we have distribution of the radial magnetic field, and on the right side, tangential components for the different parameters, value parameters of the E. Provision number 3. In the provision number 3, we have to write down the total energy density of our system, monopole plus spinor field system. And as you see, we have two like square brackets. The first bracket corresponds to the energy density of the monopole. The second one corresponds to the energy density of the spinor field. And here, as you see, we have a distribution of the energy density along the radius, also with for the different values of the parameter E. And finally, the total energy of the system, we also split it in the two forms, in the sum of energies. The first one, energy of the monopole, the second one, energy of the spinor field. And as you remember, the calculated data for the total energy of the system was presented in the table number 1. And here is the main result, which is correspond to the provision number 3. We have plotted the dependence of the total energy density as a function of parameter E. And as you see here, we have a minimum in energy spectrum. This minimum we can interpret like a mass gap. So mass gap, it's a minimum in energy spectrum. Also, we continued our searches. And as you see here, we have computed values of the total energy of the system, like a function of this dimensionless coupling constant. And for each total energy of the system, we have found minimum in energy spectrum. Why? For creating this picture, for plotting the dependence of the mass gap, so minimum in energy spectrum, on the dimensionless coupling constant. So that brings me to the end of my research. Research results number 1. So we have found regular monopole-like solutions in Yang-Mills theory, which includes spinor fields, nonlinear spinor fields. And we suppose that these solutions can describe quasi-particles, monopole and C-quarks in quark-gluon plasma. The second result, we also demonstrated that the energy spectrum of our solutions has a minimum in energy spectrum, and this minimum we can interpret like a mass gap. So this effect can be considered like a QCD effect in non-QCD theory. And the last result, we understood that the main reason for the appearance minimum in the energy spectrum was the presence of nonlinear spinor fields, which is the source of our magnetic field. Here, I would like to present you some articles which were published during 3 years of study at this university. And here, I would like to highlight articles in journal Modern Physics A, Physics Letters B, and Physical Review D. So thank you for your attention.
So the talk is over. Please, dear colleagues, feel free to ask any questions. So let me start with a couple of questions. Albina, can you show us, my first question is about your first part of investigation. Can you show this expansion of the beta function?
Mm-hmm. You mean this one?
Right here, yeah, right. So this expansion equation number 9.
9. Mm-hmm.
Is it really an expansion? Yeah. Is that correct? Mm-hmm. Yeah. But at what values of x? I mean, you didn't mention this is at very large values of x. Yeah, right?
Yes. Mm-hmm.
So this means that this beta function should vanish at very large values of x. Yeah, right? Is that what we assume to find? Yeah.
Mm-hmm. Yes. Mm-hmm.
Okay, the second question is about equation 11.
11. Sorry.
The second.
You mean this? The second. Okay. This one.
So I mean this. You show the Lagrangian here, yeah, right?
Yes.
Is it your achievement or just it's an all Lagrangian? You mentioned that the last term is a non-linear one, yeah?
Yeah, actually, I have taken this Lagrangian from the previous works of my scientific supervisor, Vladimir. And yes, so for example,
okay,
in
just
taken, and for example, in Chunshali Vladimir article, they investigated Proca field. Yeah, in our case, we investigate in Yang-Mills field. So there is a differences. There were Proca fields. In our case, Yang-Mills fields. Yeah.
Okay. Then I see. Because it was not clear what you exactly did in your research. I mean, in terms of novelty.
Yeah, I mean, yes, these equations we have taken, 11, 12, and 13, but we have obtained these equations, 17, 18, and 19, and we investigate these three equations.
Yeah, okay, you just actually found a new solution, yeah?
Yeah, new solutions, which is different from 't Hooft-Polyakov solutions, yeah.
Okay. So any other question, colleagues? Feel free to ask questions, maybe in Russian or in Kazakh. По-русски тоже можно спросить.
I've just raised my hand, but obviously you guys cannot see it. Can you?
Oh.
Yeah, okay. Yeah, feel free. Just.
All right. So I have a question about the brain part of the thesis.
Okay.
So I've noticed somewhere that solutions have some solution with anti-de Sitter asymptotics. And
yeah. Let me show you the graph. Yeah. Okay. So thank you for your question.
Well, I haven't asked it yet.
So this one, yeah, figure number 1.
Yeah. So yes, I have more general question about your solution with anti-de Sitter asymptotics, because to me, ADS asymptotics doesn't look physical. In the real world, we are mostly favoring de Sitter or flat asymptotics.
Yes.
So can you mention any application areas of your ADS asymptotical solutions?
Yeah, so thank you, Konstantin. And here I would like to explain you that we actually have found that our solution are with anti-de Sitter asymptotics, but not exactly on the brain, like you tell us. In the real world, our universe, yes, de Sitter asymptotics, but in our case, we have found anti-de Sitter asymptotics not exactly on the brain, which is we found it far away from the brain. It means we have found in multidimensional space, which is called bulk. So why? Because as you see, here is we have, let me use this one. So yeah, it's xn. If you remember, xn was in the metric. Let me show the metric. Yeah, so this is the last coordinate, fifth coordinate. So that's why we have found solutions with anti-de Sitter asymptotics not on the brain, on the fifth, on the last coordinate, which is the bulk in our case. So it's not on the brain exactly.
Okay, thank you.
Так, еще вопросы, коллеги?
Thank you.
I have several questions.
Yeah.
Okay, thank you for a nice presentation. So I have several questions. So let me start from the first part when you introduce the function as alpha r of power n. So can you explain the motivation behind the choosing of this form of the function, this fr? In the second question, what is the motivation? Why did you choose exactly this form of the function? Why don't you choose the other forms of this function?
Thank you, Ahmadjon. Yes, so let me show you the relevance of the topic. Yeah, if you remember, I have shown you these families of series, yeah, and we have chosen, yes, series with higher order derivatives, such type Why? One of the reasons that I think that it's the simplest type of modified series of gravity, which was firstly introduced by Starobinsky in 1918, because if you remember, our equations of motions become the third derivatives, and fourth derivatives, so it's much simpler to investigate equations with a third derivative of beta function. So it's much more simpler. And also the second reason, I think that effector gravity is actually well-known gravity. So many authors have studied such kind of theory. So that's why we have chosen the famous one.
Okay, so another question is more, let me say, more general, because you have two parts in your thesis. And first part, you're studying the equation, the solution of the equation in the brain model. And the second part, we're looking for the monopole solution and monopole magnetic field, magnetic monopole. The thing is how you can check with the experimental or observation data, or can you suggest at least how to test your results with the experiments or the observation, even in the future perspectives?
Thank you, Ahmadjan. Talking about the first part related to the brains, if I'm not mistaken, soon at the CERN, they're planned to conduct some experiments to verify, is our universe exactly a brain? So whether do we live on the brain or not, is our universe multidimensional or not? So at the CERN, will be conducted some experiments to verify this theory. And for example, if the law of conservation, law of energy will be violated during the scattering of the particle, so it means that the answer, where is the missed energy? So this missed energy can be carried away with the particle. So this can be some confirmation, indirect confirmation of, do we really live on the brain? So at CERN, soon will be such experiments according to the first part. Talking about the second part about monopoles, as you remember, we told, I have explained is that we consider our monopole like nonlinear spinor field like quasi-particles. So we can say that they describe quasi-particles in quark-gluon plasma, and maybe if in the future these particles can be found, and maybe these results that we have obtained in this work will understand us to investigate these particles at a deeper level. So in the future.
Since you already talked about the quasi-particles, maybe I can extend. So have you made the estimation of the energy of these quasi-particles you are suggesting?
So actually I have prepared a slide for your question, for this kind of questions about energy. So let me show you the table. Yes, as you see here is we have total energy of the system, which is dimensionless quantity. But if you, I thought that maybe there will be some questions, so that's why I tried to calculate it. Let me show you, it's the last slide I have prepared. So here, so as you see, I take such values as a parameter. This is the coupling constant, this is the Compton wavelength, this is the L0, it's in our case it's G multiplied by lambda, and as you see here I have calculated the minimum mass of the quasi-particle, we can say. So as you see, it's approximately 2 × 10⁻⁻41 gram, and I also have calculated the minimum energy for our object. Minimum energy have to be approximately 2 × 10⁻⁻20 erg. So this is the minimum value. So and for this value, I have taken energy, as you see from this table. Let me show you one more time. So I have taken here the value from here, 50. I have taken 50. And substituted to the equations and substituted and estimated that the minimum energy will be 2 × 10⁻⁻20 erg. So minimum energy.
Okay, thank you.
Thank you.
So any other questions?
Sorry, can I ask you?
Yeah.
What energy need in experiment if you wish to see this monopole or brain, for example? Where our back can see your particle, quasi-particle, or big hadron collider?
Yeah, it's really hard question because these quasi-particles, they are hypothetical particles. But we suppose if these particles will be found in the future as a hadron collider, maybe they will have such values of the energy. Yeah, so for the ground state, these values, and for the first values, these.
Yes, this energy, but what energy need experimental? What now it's 20, I don't remember.
I think that actually I have read a lot of articles about monopoles, and I have written that I have read that monopoles actually they're very like heavy particles, have to be with the mass like 10 in the power 17 giga-electron volt. So for these heavy particles, it is needed a lot of energy, which is not we don't have in the hadron collider, for example, yeah. So that's why one of the reasons for explanation, it's like these particles, monopoles, I mean, could be existed at the early time after Big Bang, maybe when the universe was very hot. So at that time, these particles could exist. But in our case, in hadron collider, we don't have such kind of amount of energy to create such heavy monopoles. So I think that is a problem nowadays.
We don't have this energy, but what energy? What?
Yeah, so sorry, I don't remember the number.
No, only very round.
So I think that 10 in the power 17 maybe, yeah? 10 in the power 17 giga-electron volt. I think so, if I'm not mistaken.
Electron volt.
Yeah, electron volt, yeah.
Maybe in cosmic.
Yeah, in cosmic, like cosmic monopoles, they sometimes called like cosmic, yeah. Or good monopoles, I have read that.
Можно задать вопрос на русском или на казахском?
Да, можно, пожалуйста.
На русском, да?
Можно, да, на русском.
Понятно будет, да, на русском?
Да, конечно.
Я хочу знать, интересная работа, конечно, огромная. Вот монополии замкнутые линии возникают на бранах, которые разделены. Ну, плоскости вот эти у вас есть. Они дискретно разделены, но соединяются какой-то синей линией. Что за линия синяя? Вот у вас там, где вы браны нарисовали. У вас есть презентации, где папки какие-то, вот и они соединены. Вот это.
You mean, окей,
Что значит синие линии?
Извините, да. Смотрите, у нас концепция браны, она очень популярна не только в общей теории относительности, но и в теории струн. То есть вот этот рисунок, он относится больше к теории струн, где вот это розовое – это брана сама, да, плоскость, вот эта поверхность, а вот это синие – это струны, которые прикрепляются, концы которых прикрепляются к этой бране. И эта брана предполагается,
просто это двумерно, это одномерно. Да, дальше. Да. Что же получается тогда? Вообще, все это имеет отношение к темной материи? Какое-то вот обоснование можно отсюда вытащить? Я сам подумаю так. Если вот у вас уравнение, что логично вроде бы, какие-то вот распределения вы нашли, это хорошо. Возникает простой вопрос. Темная материя, исходя из этого, может быть, ну, классический термин, пористой, разделены размерностями. Вот двумерная отделена от одномерной какими-то полосами. И тогда, если темная материя представить себя как пористый, ну, разной там, ну, размерностями, тогда очень интересно, правдоподобно можно подумать с точки зрения известных разделов физики. В общем, кто-то, я вот это автор когда-то читал, вот это Аркани, там, они там писали, когда большие размерности можно объяснить так. Они писали много измерений, так, многомерные и так далее, и так далее. Ну, конкретно. То есть я не затрудняю вас, я для себя спрашиваю. Если монополии замкнутыми линиями созданы как на ограничениях размерностях, на двумерных, одна монополия, одномерная, ну, одномерную монополию я не понимаю, как она может. Ну, в всяком случае, они должны замыкаться. А вот, да, замыкание. Что-то есть тогда. Итак, простой вопрос, или ответ будет, или непонятно будет, все равно я спрашиваю. Все люди занимаются сейчас темной материей. Темная энергия даже менее интересна, по крайней мере для меня, как преподавателя. А вот темная материя, вот это, наверное, что-то ближе будет. Какие-то обзоры говорят люди об этом. Вот. Я вставлю свой вопрос, не то что вопрос, утверждение свое вот, для обсуждения. Вот темная материя, если она есть, если она поддается к обычному толкованию, то она может быть вот такой дырявой, с разной размерностью. Тогда что-то может быть. Так или не так, не знаю. Как вы думаете, в конце концов?
Смотрите, если честно, я когда делала литературный обзор по теме Бран, да, я видела, что множество статей пытаются объяснить с помощью модифицированной теории, да, с помощью Бран темную материю, то есть вращение галактик. Да. Я даже себе один раз выписала этих авторов, просто сейчас не могу вспомнить, извините. И там, да, действительно, они вводят Yukawa term, член какой-то Юкава, гравитационный потенциал, чтобы объяснить вот эту вот темную материю. Да, такое я читала, просто, если честно, я забыла авторов, кто занимался этим. Ну, работ очень много, да, которые объясняют с помощью Бран, с помощью модифицированной теории гравитации темную материю. Да.
Понятно.
Да.
Спасибо. Что-то есть.
Спасибо.
Это какой-то хоть непонятный, но логика позволяет так думать. Спасибо, ладно.
Да. Спасибо.
Карл Баланович, я хотела задать вопрос.
Пожалуйста, да.
Ну, я занимаюсь совсем другими вещами, но я вижу, что Альбина, так сказать, глубоко в теме, поэтому вопросы у меня очень простые для нее будут. Вот в названии вашей диссертации мне встретились два новых понятия. Это монополия, ну, магнитная монополия, и браны. Вот какой физический смысл вы вкладываете вот в эти два понятия? Обладают ли они массой, зарядом? Подчиняются ли законам квантовой механики? Эти вопросы для вас простые, надеюсь получить хорошие ответы, ясные, простым языком.
Смотрите, эти объекты, мы считаем, что это гипотетические объекты, потому что до сих пор, к сожалению, экспериментально не удалось подтвердить, что наша Вселенная — это прана, которая вложена в многомерное пространство, время. Что касается вот второй части, да, были посчитаны даже массы, могу даже показать вам значение. Сейчас, извиняюсь, еще раз покажу. Да, вот, например, мы посчитали массу этой квазичастицы, то есть она примерно вот этого значения, и мы посчитали энергию. Ну, так как я знаю, что магнитные монополии — это вот, очень стабильные частицы, когда я делала литературный обзор, говорилось, что это очень стабильные частицы, которые, да, обладают массой, обладают зарядом, причем заряд, например, монополя 70 раз больше заряда электрона, что еще. Также посчитано, что с помощью вот этого магнитного заряда можно объяснить квантование электрического заряда. Вот. Он не принимает заряд монополя, он не принимает какие-то любые значения, он принимает некие дискретные целые значения, кратные значения от элементарного магнитного заряда. Что еще про магнитные монополии известно на данный момент? То, что это очень стабильные частицы, и они могут распадаться на более мелкие только когда, вот, например, аннигилируют два монополя, например, да, а так это очень стабильные частицы. Вот, то есть вот этот вот литобзор, по литобзору я вот могу сказать вот эти вот данные, пока известны.
Пример браны можете привести?
Про браны, да. Про браны, да, к сожалению, бран это более такой сложный для меня объект. Сейчас про браны. Что я могу сказать про браны, то, что нам известно на данный момент, это то, что брана, наша Вселенная рассматривается как брана, то есть четырехмерная поверхность, извиняюсь, да, поверхность, и с помощью этой браны, оказывается, можно объяснить иерархию элементарных частиц, да. Так, что еще? Да, про браны, если честно, извините. Да, если честно, да, вот этих значений я, когда делала литобзор, не встречала никаких данных.
Подчиняются они законам квантовой механики?
Да, я думаю...
Думаете или подчиняются?
Если это брана будет рассматриваться как наша Вселенная, то, я думаю, все законы, закон сохранения энергии, импульса и законы квантовой механики будут выполняться.
А точка – это брана?
Точка, да, смотрите, браны бывают разных видов в зависимости от размерности. Есть вот то, что вы говорите, точка, это называется DO, то есть нолик. Это означает, что это точка. D1 – это там линия, да, какая-то прямая, там, D2 – там двухмерная плоскость, да, и так далее. Да, то есть
скажите, а вот вы говорите, что брана и монополии, они не обнаружены. А что будет с физическими законами, если они будут обнаружены?
С физическими законами? Возможно, касательно браны.
Ну ладно, подумайте. Спасибо.
Да, спасибо вам за вопросы, интересные вопросы.
So I think it's enough with the question. Yeah, no objection, dear colleagues.
Yes, Professor Smeton.
Слышно?
Профессор Склитон.
Пожалуйста, хотите спросить, да?
Профессор Склитон, думал, хотел просить.
Douglas, yes, Douglas.
Okay, yeah, so thank you for a very nice talk. Actually, I did have one question. Normally, a TÜV Polyakov monopole has a radial magnetic field that has a 1/r² behavior and no theta, no angular components, right? And so now your solution had a radial component that had a 1/r³ dependence and actually did have theta and phi components, so did have angular components. So in that sense, is a little bit different than a TÜV Polyakov monopole. So actually, this is very interesting. Do you have any explanation or any physical motivation for why this happened in your solution?
Yeah, so thank you, Douglas. Yeah, as I told you, in our monopole-like solutions, asymptotical behavior of radial magnetic fields, which looks like dipole, not monopole-like objects. So actually, yeah, so maybe we suppose maybe there are like two monopoles at some distance, yeah, located at some string, maybe we suppose like that. And here is why we have such kind of asymptotic behavior of the radial magnetic field and why we have tangential components. It's because that we don't use triplet of the Higgs field like was in the Hooft-Polyakov monopole. In our case, the source of the monopole-like solutions were doublet of the nonlinear spinor fields. So that's why I think that it's because of the using different sources of magnetic fields. Yeah, so that's why our behavior is different from Hooft-Polyakov monopole. Yeah, so there is no exact answer actually because they're hypothetical objects, quasi-particles.
No, that's a good answer. Thank you very much.
Thank you, too.
So any other questions, dear colleagues?
May I ask too?
Yeah, okay.
Thank you. You wrote for modified gravity that your n is below 2. What reason for choosing this physical minimum?
Excuse me, Kaplan Dejan, I didn't catch your question, sorry.
Окей. Вот у вас было в показателе степени n меньше 2,
Да.
от 1 до 2 в модифицированной гравитации. Да.
Ага, вот.
Почему вы выбрали такую модель? Спасибо.
Мы не выбирали эту модель, это получилось в результате метода неопределенных коэффициентов. То есть, смотрите, когда мы подставили вот это разложение номер 9 в основное уравнение номер 8, и для того, чтобы обеспечить конечность производных, ведь у нас производные третьего порядка, мы приравняли коэффициенты вот третьей производной, дельта минус 3, чтобы обеспечить конечность, и получили выражение для дельты. Именно вот эта дельта и вот условие того, что мы хотим обеспечить конечность уравнения 8, конечность производных, привело нас к этому условию. То есть мы это не выбирали, это как бы следствие решения этого уравнения.
Thank you very much.
Any other questions?
Добрый день, меня слышно?
Да, слышно, да.
Это Рашид Валиуллин, член Совета. У меня было два вопроса. Первый. В чем состоит особенность обнаруженной вами точки в центре браны? То есть что это? Сингулярность, неустойчивость или скачок плотности?
Вы имеете... Ага, да, вот этот рисунок, да, где фазовый портрет вы имеете, да?
Да.
Так, сейчас. Ага. Да, в этом портрете, да, действительно видно вот эти вот особые точки, да, мы называем его центром браны. То есть, ну, я как понимаю, если честно, вот зачем нам даются фазовые портреты? Фазовые портреты даются для того, чтобы построить зависимость двух величин, например, в нашем случае это бета double prime, бета prime. Например, в механике, да, фазовые портреты строятся там для координаты, для скорости, которая первая ее производная, там, в электричестве заряд и ток. То есть фазовые портреты, они показывают особые точки, в данном случае это, да, вот эти вот наши точки, откуда, как бы, получается, выходят вот эти вот фазовые линии, вот эти вот, да, то есть это как бы траектория. Я считаю, что, возможно, эти точки, они как бы символизируют, вот когда мы решаем дифференциальные уравнения, мы задаем там начальные условия, и вот при данных начальных условиях фазовые линии выходят из этой особой точки, которая описывает траекторию фазовых линий. То есть, скорее всего, это больше имеет смысл к траектории. Скорее всего, да. И...
Хорошо. Еще второй вопрос. Значит, особенностью обсуждаемого вами подхода является использование многомерного формализма.
Да.
Когда возникает вопрос, о каком реальном числе измерений может идти речь и насколько это физически обосновано?
Ну, если мы говорим о бране, да, то да, мы говорим, что наша Вселенная представляется собой брану, то есть, скорее всего, мы должны рассматривать четырехмерное пространство-время, но никто, в принципе, не против, ну, так сказать, не был, извините, сейчас. То есть наша Вселенная рассматривается как четырехмерное пространство-время, поэтому я считаю, что было бы логичнее рассмотреть именно четырехмерное пространство-время. Да. Но все-таки о других дополнительных измерениях их нельзя отбрасывать, ведь все-таки теория многомерности пространства-времени, она еще на стадии изучения, и, возможно, действительно мы живем, мы вместе с браной локализованы, так скажем, в многомерном пространстве в балке. То есть здесь такой вопрос, что, скорее всего, да, лучше рассматривать четырехмерное пространство-время, но все-таки дополнительные измерения тоже было бы интересно рассмотреть.
Хорошо, спасибо.
Я думаю, да, так.
Я все.
Спасибо большое за вопрос.
Так, еще вопросы есть, коллеги? So I think it's enough with the questions. Yeah. Let's continue our meeting. So the floor is given to the domestic scientific supervisor, Doctor of Physical and Mathematical Sciences, Vladimir Junushaliev. Please.
Okay, so the dissertation of Albina Serikbolova has two parts. In the first one, she considered the solutions in multidimensional gravity, so-called SIG-brain solutions. And the most important feature of this solution is that this vacuum solution. Because let me compare the situation with general relativity. In general relativity, we should have some kind of matter to obtain some non-trivial solution. So, and she obtained vacuum solution, and this is I think that is most interesting in this in the first part of your investigation. So, and physical application is this is for such SIG brain solution we can realize brain world scenario. So, in the second part of this dissertation, she considered SU2 non-abelian gauge theory, whereas the source of gauge fields is doublet of nonlinear spinor field. So, and the most interesting thing, here is that the energy spectrum of such monopole-like solution, it has global minimum, which can be named as mass gap. So why this is interesting? Because the problem of mass gap is one of the most important problems in modern theoretical physics. And let me finally, so I have to read my conclusions. I believe that the dissertation of Serikbolova, Albina Skana, brains and monopoles in modified gravities in Young-Mills series meets the qualification required for dissertation for the degree of Doctor of Philosophy, and its authors deserves to be awarded the degree of the Doctor of Philosophy in 8D05306 physics. Okay.
Thank you. So, dear colleagues, we have received a review of the foreign scientific supervisor Jutta Kunz-Dolschagin from Germany. So let me not to read it completely because it also describes the structure of the thesis, which is now obvious for us. So let me read just the conclusion. Quote, in conclusion, I would like to say that Mrs. Albina Serikbolova has performed an impressive amount of difficult original research that has been published in 3 well-known international journals. She has shown full mastery of the field on the theoretical side, and she has performed numerous challenging numerical calculations. Therefore, the thesis satisfies the highest requirements of doctoral dissertations, and Mrs. Albina Serikbolova certainly deserves to be awarded the degree of Doctor of Philosophy in specialty physics. End of quote. So, the next floor is given to official reviewer, PhD at the Institute of System Sciences, German University of Technology, Konstantin Zloschastyev. Please.
Thank you very much. Oh, I can hear noise. Okay, cool. Can you hear me?
Yes.
Good. Okay, where do I begin? All right, so dissertation of Serikbolova Albina corresponds to the priority direction of development of science, and which is widely supported by the granting bodies of Republic of the Kazakhstan. And I must say that results presented in the thesis, they have theoretical significance within the corresponding area of research. The importance of obtained results is well disclosed, and relevance of thesis studies is justified by examining some topical issues of modern mathematical physics related to the study of the minimum in the energy spectrum of the hypothetical monopole-like objects with a nonlinear spinor source and objects in multidimensional space, which are called branes, within the framework of the modified theory of gravity. And branes, for example, are currently still popular conjectured objects. Therefore, studying their properties is a valid problem, in my opinion. And the relevance of studies of magnetic monopoles lies within the framework of the Yang-Mills theory, including nonlinear, which in presence nonlinear spinor fields, and thesis has novelty in finding the minimum in the energy spectrum of the solution. As supervisor said, that this and further justifications are supported by the publications of research results in high-ranked journals. What else can we say? All right, so just enumerate the novelty of the thesis. So number one is new flat symmetric solutions in multidimensional modified theories of gravity for branes are obtained. Second, it is demonstrated that the main reason of a minimum occurrence in the energy spectrum in monopole-like solutions, SU2 Yang-Mills theory, was the presence of a doublet of nonlinear spinor field. And number three, it is shown that Yang-Mills monopole with the source of nonlinear spinor field differs from the Dirac and 't-Polakov monopole. And the conclusions of the thesis are well justified from a scientific point of view. All right. And I have some additional remark, which mostly for future extension and development of her work, and which concerns mostly the monopole part of this thesis, because I noticed that it refers to some superfluidity and Bose-Einstein condensation phenomena. However, those monopole solutions which were obtained in superfluid droplets or whatever, they're mostly they're sort of effective monopoles. There is no real monopoles there, and this mostly like an analogous phenomena. Therefore, it would be interesting to consider a realistic superfluids, like similar to the laboratory superfluids. Maybe it could be a superfluid helium, and we know that the models they successfully involved so-called logarithmic superfluid models because it's some particular type of superfluid models which in
I think that the internet is breakout.
Он звук выключил. Звук выключил.
Выключил или совсем пропала связь?
Мне кажется, что-то со связью.
Нет, он выключил просто, может готовиться. Ну вот сейчас он открыл.
Нет, он вышел.
Okay, it seems I'm back. I'm back.
Okay.
All right. So let me just repeat my final remark about the logarithmic superfluid extension of possible extension of the work. Because in a theory of laboratory superfluids, I mean, which is, as you know, is very down to earth and very pragmatic in studying, because people are studying in speed of sound and they must produce very precise fitting curves for the phenomena they see in superfluid helium, for example. So in those theories, in those models, there's quite popular models which have logarithmic nonlinearity. And if you translate those models into the relativistic case, just for interest of it, then it's basically you're considering logarithmic nonlinear scalar fields. So that would be interesting to study your monopole solutions with, of course, spinor solutions if you want to, plus those logarithmic nonlinear scalar fields. And then would give you extra motivation and say extra justification of to the physicality of your results. All right, so, but this is, of course, my remarks are just recommendatory. They just designed for future direction of the research work. All right, so to summarize, the thesis by Serikbolova Alina Askarovna, which is entitled Brains and Monopoly, Modified Gravities and Yang-Mills Theories, has been performed at a proper theoretical scientific level. It is a completed research. Its content and design meet the requirements of the Committee for Control in the Field of Education and Science of the Ministry of Education and Science of the Republic of Kazakhstan to PhD dissertations. And its author, Serikbolova Albina, deserves to be awarded the degree of Doctor of Philosophy, aka PhD, in the specialty AD 05306-physics. Thank you very much.
Thank you. So Albina, are you familiar with the remarks given by the reviewer? Can you reply to them?
So talking about the monopole solutions with including logarithmic nonlinearity scalar fields, my scientific supervisor told me that he investigated approximately such kind of solutions. So with including logarithmically nonlinear scalar fields, which looks like a Mexican hat. So, and yeah, I think that it would be great in the future direction to investigate such solutions, which describe superfluid and Bose-Einstein condensate, because as you remember in the relevance, I have shown you that there are interesting searches for magnetic monopoles in Bose-Einstein condensate or in the like superfluid helium droplets behave like magnetic monopoles. So yes, and for example, scientists from Boston created, they modeled synthetic magnetic monopole in Bose-Einstein condensate. So that's why I think that, yes, if we include that term, if we investigate monopole solutions with logarithmically nonlinear term, it will definitely theoretically describe magnetic monopoles. Yeah.
Okay, Konstantin, are you satisfied with the answers?
Yes, thank you very much.
Okay, yeah, the next floor is given to the official reviewer, Professor Singleton, please. Douglas, can you hear us?
Yeah, hold on just a second. Okay, sorry.
Okay.
Yeah, so
you can stay only on your maybe some comments or criticism and just the main conclusion. You don't have to read your review as a whole.
Okay, so I thought the research was well researched. It was important work, novel work, dealing with brain world solutions and monopole solutions in Yang-Mills theories with nonlinear spinor fields. So on the whole, the dissertation work of Serikbolova Albina Ashkarnova on the theme of brains and monopoles in modified gravities and Yang-Mills theories, performed at a high scientific level in a completed independent research work in content and design, meets the requirements of the Committee for Control in the Field of Education and Science of the Ministry of Education and Science of the Republic of Kazakhstan, 2 PhD dissertations, and its author undoubtedly deserves to be awarded the degree of Doctor of Philosophy in the specialty 8D05306 in physics.
Thank you very much. So, dear colleagues, we have finished with the official reviewers. Any other opinions on this dissertation? Yeah, or defense maybe. So any member can give us an opinion. Так, коллеги, кто-то хочет высказаться еще? Ни у кого не сложилось какого-либо мнения? А? Можно по-русски, можно по-английски. Ограничений нет, коллеги. So let me start with the discussion. So I think that Albina today demonstrated quite a good knowledge of her work. This was really impressive. Her answers were very concrete in some sense. You know, of course, there are some problems with physical understanding and describing the appearance of such hypothetical objects in real nature and real experiments. But first of all, I think that the whole thesis is very, very good in terms of scientific quality, because the results were well published in peer-reviewed journals. And the second thing is that it seems like she did all the work by herself, and she's very competent in answering questions and in presenting material. I think this is an obvious thing, so that I completely support the reviewers' opinions that we have to grant her a PhD degree in physics. So any other opinions, dear colleagues? Feel free, do just a few words.
Let me say.
Yeah, okay.
Okay, so actually, I think I know Albina from our joint seminar, from Uzbek-Kazakh joint seminar, and she presented her preliminary results, I think, last year or even before the last year. And at that time, it was very hot discussion. And now I can see that since that, so Albina worked very hard on her results and on her type and on her style of presentation. And now I see that she learned a lot during the last years, and now she can clearly present, and even as mentioned previous speaker about the physical cases. Of course, there are some let me say some unclearance in the physical application, but still, since it is a theoretical physics, hopefully in the future we will have some physical and astrophysical confirmation of the results. And but saying about the defender, I think she meets all the criteria, and she deserves to be granted with the PhD degree. I support her.
Thank you very much. Any other opinions, dear colleagues?
Можно сказать просто?
Да, пожалуйста.
Задачи, которые рассматривала Альбина, они относятся к космологии, и вводя вот какие-то дополнительные координаты, пространство многомерное, ну, физики пытаются объяснить проблемы происхождения, эволюции Вселенной. Конечно, такие вопросы интересны всем, не только физикам. Вот в этой связи тема диссертации, конечно, интересная и актуальна. Считаю, что диссертация справилась с поставленной задачей, грамотно отвечала на вопросы, сделала прекрасную презентацию. Но хочу добавить, что очень приятно, что выпускники нашего факультета вот занимаются решением таких задач современной космологии. Но это, конечно, благодаря их научным руководителям. Они подрастут и вовлекут следующее поколение казахстанских выпускников нашего факультета. Это отрадно. Считаю, что Серикболова Альбина заслуживает присуждения степени доктора философии по специальности физика. Я буду голосовать за предоставление ей этой степени. Спасибо.
Спасибо. Any other opinions, colleagues? Кто еще хочет высказаться? Достаточно, наверное, тогда, да? So, thank you very much, dear colleagues. Let's move on to the next step of our meeting, which is an electronic vote. I've been said that you are all familiar with the procedure yet. So now we have to check our emails where we should find a Google form for our vote. Коллеги, давайте
Voting ballots have been sent to your mail address. Can you vote, please?
Все, я проголосовал.
А как голосовать, я не совсем понимаю.
Надо зайти на электронную почту. Зашли, да?
Сейчас не нашел.
Gmail почту зайдите, пожалуйста.
Понял, все понял.
Были отправлены все.
Там он обычно падает в промо-акции, если это Gmail. Это Google форма.
Так.
Если в входящих письмах не найдете, ищите промо-акции, спам можно посмотреть или...
Все, нашел, все, спасибо.
Там надо обязательно один из вариантов.
Ага, понял. Сейчас проголосуем.
Я проголосовал для информации.
Проголосовал.
Так, я тоже проголосовал.
Восемь человек проголосовали. 8.
Ардалаш Нурмана там.
Тише, дорога.
Десять. 2 человека. Хорош, нормально проголосовала, пишет. Ага. Двоих ждем. Зинол Жанабаевич, голосовать ettiniz mi?
Нет, Фарид, я проголосовал. Пошло, нет?
Фарида, я
Там не видно,
проголосовала.
дошло. Там не видно, от кого он
Да,
такой.
анонимно. Кублан Канаевич, проголосовали?
Да.
Спасибо. Рашид Равильевич,
Да, я проголосовал.
Павел Михайлович,
Я же сказал, I'm voted. Yes.
Ахмадшон Абдужанович,
Тоже проголосовал.
Игорь Александрович,
Да, проголосовал.
Константин.
Ревьюеры же не должны голосовать, да?
Должны.
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 Рецензенты тоже. Вот Дуглас Александр.
Окей.
Наверное, вот они двое не проголосовали.
Да, вот меня спрашивают, должен ли. Я сказал, что нет, сейчас еще раз напишу.
Нет, почему? Мы когда пробное голосование проводили, они проголосовали, так что они все знают.
Так, а они здесь, да? Или вышли?
Я не знаю.
Ну, профессор Синглтон здесь, ну и второй здесь, да. Но они не проголосовали, по-моему.
Окей. Даг, you have to vote also. And Kostya,
Yeah. So yeah, that's what I was asking. So I didn't receive anything in my Gmail.
So you have to check not your, let me see, this Google form can fall into the subdirectories, you know, like promo actions and that sort of thing. You have to check everything.
Okay, so you sent, all right, so I'm in my Gmail account. So,
Gmail.com.
Yeah.
На Gmail.com были отправлены.
Check the promo.
Action.
Посмотреть теперь.
Right, so yeah, I don't see it. So there was an earlier email like 7 days ago from
right.
Marita, and then I replied I received it, but now like, and yeah, I'm looking at all the promotions, the social, the primary account. There's nothing.
Фарида, проверь. Он говорит, там нету ничего.
Нет, k.j.zlочастев @gmail.com.
Нет. Это Дуглас говорит.
Send it to the send the Google
Подождите, тогда douglas.singleton @gmail.com было.
Send it to this email. Hold on, I'm putting it in the chat.
Не, он видит предыдущие письма. Да, сегодняшний.
Yeah, send it to that email.
Что он не видит?
Вот он тебе другой email послал.
Look in the chat. It's in the chat.
Чат посмотри, другой email.
Вот douglas.singleton @gmail.com было отправлено.
Я могу ему переслать ссылку? Попробовать?
Нет, давайте я еще раз на это.
На другой email.
Он другой email в чате написал. Он чат, видишь, красненьким горит возле зелененького. В зуме.
Хорошо.
Professor Singleton, in any case, I have opened this Gmail when I choose not all paper.
Yeah.
All post in Gmail.
Отправила.
На новый, да?
Да.
Okay, I got it.
Okay.
Но все равно
Very good, yeah.
Нет, но все равно
Получился.
ответ 10, все равно 2 человека не проголосовали.
Сейчас проголосуют 11, кто-то еще не проголосовал.
Нет, а вот Константин не проголосовал.
Он мне написал, что проголосовал.
Проголосовал.
Но
Я даже скрин сбросил в этом, в WhatsApp-группу.
У нас все время вот такой.
вот теперь 11, да. Ну, 1 человек.
Okay, so I just
Thank
said
you,
my
Doc.
vote.
We got
Okay.
your vote. Yeah.
Okay, great.
Thank you.
Sorry.
Карандашом керек.
Ну, оставим тогда так и есть, да?
Сейчас экран виден, да?
Да,
У
да,
нас
да.
экрана. Да, вот голосование Серикболовой Альбины Оскаровны. Ответов 11. Сейчас. Вот 11 ответов присудить.
Да?
Да, все 100%, 11 человек 100% за присудить степень доктора философии. Но получается, один ответ, как пишем, Оскар Иванович, что бюллетень
Воздержался.
воздержался.
Нету его бюллетеня.
1 человек воздержался, 11 членов за присудить степень доктора.
So, let me announce the voting results. All the members of the dissertation, not all the members of the dissertation council voted successfully, unfortunately. So the results of the voting is as follows: in favor of granting the PhD degree, 11; in favor of revision, 0; in favor of redefense, 0; in favor of refusing to grant the PhD, 0. So therefore, the Dissertation Tribunal of Al-Farabi Kazakh National University in the group of specialties physics, nuclear physics, technical physics, physics, astronomy, radio engineering, electronics and telecommunications, material sciences and technology of new materials, like heat power engineering, physics, has decided to grant to Albina Serikbolova the degree of philosophy in the specialty physics. Congratulations.
Thank you.
Поздравляю.
Спасибо.
According to the rules, we have to approve our final conclusions on the thesis. You all were provided with a draft, but I suggest that if you have any comments, you just email them to us. Okay, no objections? No objections. So the tribunal meeting for the defense of the thesis by Albina Serikbolova is declared closed. Thank you very much for your participation, dear colleagues.
Thank you and congratulations.
Thank you so much.
Congratulations.
Thank you.
Bye.
Поздравления.
May I tell something?
Yeah.
If you don't mind. So I would like to say thank you so, very much for the members of the Dissertation Council for finding time, for collaborating with me. So especially I would like to say thank you Farida Bilisarovna and Oskar Tavletov, and also I would like to say thank you to the official reviewers, to the Защита Konstantin and to the Douglas, because you have found opportunity to be familiarized with my work, and with the help of you, I have improved my presentation and my work as well. So, and also, especially big thanks for scientific supervisor, Jimshali Vladimir Kadirovich, because you gave me a lot of advices, you gave me a lot of guidance, and without you, I think that I will not be able to reach such high level of results. So thank you for you.
Thank you.
Thank you. Так, можно, наверное, остановить запись, да?
Да, останавливаю запись.
Ага, имитирую. Все, спасибо, коллеги.
Спасибо большое.
Всем спасибо.
Фарида, следующий же у нас в час, да?
В час встречаемся, да. В час.
Да? Хорошо.
Спасибо.
Даня.
Интересно.
До свидания.
Спасибо большое.
До свидания.
До свидания.
Удачи.